Thank you so much for joining this virtual workshop session.
Buenas, ahí está, ahora sí. Miren todo el setup, ¿no? La tele, ahí el loguito LED que tenemos para el stream. No sé si se me ve bien. Ahora ya somos 28 live, así que en cualquier momento el video directamente. Si se me escucha, pongan pulgar para arriba, comenten. Y si tienen preguntas, también pueden hacerlas. Y bueno, nada, después serán respondidas por parte del equipo de Project. La siguiente charla, vamos a presentarla como... Tenemos todavía más, estamos un poco atrasados con las charlas, hay que ser sinceros, pero tenemos mucho para dar y todos quieren hablar un montón, hay muchos premios, entonces... Nada, cosas que pasan qué cosas. Bien, la siguiente charla es de la gente de ZKM Project y la host o speaker es Alice Liu. Así que nada, chicos, los dejo con esta charla y nos vemos pronto.
Thank you so much for joining this virtual workshop session. My name is Alice. I am education lead at ZKM, and we're very excited, the ZKM team, to be sponsoring a track at Ethereum Argentina. So thank you, everyone who is watching this workshop today. We're going to dive all into what Zyren is about. So Zyren is ZKM's ZKVM. It's a MIPS-based ZKVM for verifiable computation. So I'll first be giving an introduction to Zyron, and then we'll be going through a walkthrough demo of how you can use Zyron for your application. And then we'll be going through some example use cases for the hackathon. Now, first, what is Zyron? Zyron is the first production-ready open source ZKVM supporting the MIPS 32 instruction set architecture for verifiable computation. And one of the main use cases that Zyron is building is the entangled rollup protocol. And it uses Zyron for native asset transfer and also cross-chain messaging without having to implement the traditional bridge architecture, which has its own security assumptions attached to it. And so with entangled rollup, we're able to use the properties for ZK for this cross-chain messaging without having to rely on these third-party bridges. And Goat Network is the first L2 unentangled rollup utilizing Zyron for proof generation. And Zyron additionally offers very comprehensive developer tooling and a proof network as well for outsourcing proof generation. And we also have a very strong focus in developer education. So one of the main design considerations that the team has made going into building this ZKVM is the instruction set architecture. So Zyron specifically uses MIPS. A lot of other ZKVMs in the market uses RISC-V, and some ZKVMs use their own custom architecture set. And the reasons why we chose to use MIPS as opposed to some of the other ISAs that are out there. First, MIPS has a pretty stable design. So compared to, say, having to use some EVM-based machine, we can prevent the need of frequently redesigning our ZKP circuits. EVM bytecode as well may undergo some frequent opcode changes. We've seen quite a lot in the past, and that's why we're seeing a trend of a lot of ZK EVMs moving towards becoming a more general purpose ZKVM. So MIPS is also simple, doesn't have any custom instructions. And additionally, MIPS has a very mature ecosystem, has a very strong industry presence. It's been around for almost 4 decades now, with a wide range of available compilers, wide range of available production use cases as well. And even for some compatibility use cases, like for example, with Optimism's fraud-proof VM, which is also MIPS-based. And another subtlety is that MIPS is very instruction efficient. So there are some special MIPS instructions, like for example, the multiply add and multiply subtract operations, and that basically combines those two operations together, and it can greatly reduce the guest program's execution trace and the number of underlying instructions that have to be proven in the ZKVM for greater proving efficiency. So we can anticipate a bit faster proving and potentially cheaper proving as well. So with all of these combined, the team chose to implement this ZKVM with MIPS specifically. And going into some more details of what a ZKVM actually entails, before I go into all of that, I'll first review what a VM is. So a VM you can think of as a program that's able to run other programs. So for example, the EVM is just a VM that can run Ethereum-based smart contracts. So within our VM, we would have some sort of initial state, some sort of input. We would have a program. That input in that program is fed into the VM, and what's outputted is some kind of final state. ZKVM, on the other hand, it incorporates all of the components of what we've seen with a VM with a few extra parts. So a ZKVM is a VM implemented as a circuit for a ZK system. It's a ZK circuit that runs a VM, and ZKVMs itself can be thought of as universal circuits because you don't have to define or write new circuits for every application that you write. Instead, every application can be represented as some kind of set of programs that can be fed into a single ZKVM, and what's outputted is that final state as well as an accompanying proof. So just as an overview, when we looked at the VM example from the last slide, we saw that there was an input or initial state, the program, and then for a ZKVM, we also have the witness. And this witness is the set of constraints that this program can satisfy. And that may also include some secret inputs or any kind of private information, private data that you don't want anyone else to read and just to be kept private. So all of these combined with the input, the program, and that witness, they're all fed into the ZKVM. And what's outputted is that final state as well as an accompanying proof that proves that the execution of that program that we fed into the ZKVM, as well as the witness, all of that corresponding is valid. And so some of the main building blocks that are contained within ZKVMs, we have the compiler. So that's just compiles a higher level language that you write your program into bytecode that's readable to the VM. The VM itself will execute that compiled program and generate an execution trace for the prover to read. And that prover will take that execution trace and generate a proof that proves each instruction within that trace. And then for the final step, this is external to the ZKVM itself, but the verifier will take that proof that the prover generated and verify it. And this can be done in a variety of ways. It can be done on-chain by deploying a smart contract. It can be done by sending it to a verification layer, or even off-chain. And so this is the main overarching kind of like bird's eye view of what the ZKVM's role is in this. So we have our program that's fed into the compiler, and that compiler will compile our program to MIPS-based instructions, and that, as well as any inputs, are fed into the VM. What's outputted from the VM is that final state, but the VM also outputs this trace record that's fed into the ZKVM for the prover to read and then finally generate a proof. So this is the entire pipeline just from a bird's eye view. And if we look at ZKVMs in larger picture, we've seen just for the past couple of decades or so, we've seen a trend of becoming more generalizable. So initially, there was a very steep learning curve when using ZK, because essentially at that time, for any application that you wanted to prove, you would have to define that application in terms of handwritten circuits. So developers had to directly handwrite these circuits in terms of their constraints, and this had a very steep learning curve attached to it. Some cryptography math background was needed, and there's only, I believe, just a couple of thousand people in the world who know how to write these ZK circuits. So there was quite a steep learning curve attached to it, but then came the development of more circuit libraries. So these were pre-built circuits for any kind of common cryptographic primitives. So in this case, developers didn't have to exactly write or develop their circuits completely from scratch. And then we became a little more generalizable. So developers with ZK DSLs, domain-specific languages, now they don't need to write circuits anymore. Instead, they can write programs in more familiar language styles that they're used to. For example, Noir, which is Aztec's ZK DSL, really tries to replicate the Rust-like syntax. And then there's some other ZK DSLs that exist as well. And then from there, we have seen more ZKVMs develop. So ZKVMs, now we can write programs in existing languages that we're already familiar with. For example, most ZKVMs in the market are compatible with Rust. For Zyren itself, we're compatible for Rust as well as Golang. And you can just be able to write these programs in languages that you're familiar with without having any kind of prior knowledge in terms of how ZK works or how to write these circuits. All that circuit writing is done for you. All you need to know is what you want to use ZK to integrate in your application for. And there's quite a lot of ZK VMs in the market today. And so now in terms of this Zyren step-by-step process, this is the overall kind of steps that Zyren goes into. And we can separate all of this into three main parts. First is the program execution, and then the second stage is the proof generation, and then the final stage is the proof verification. So for the program execution, essentially a program is written in some kind of higher level language. So right now, as I mentioned before, Zyren is compatible with both Go and Rust. And then the program with the MIPS compiler, it's compiled to an ELF binary, and the ELF is just the executable format for the MIPS instruction set. And the main purpose here, we're just converting that source code into machine readable code that's readable to the VM. And then we'll take that binary file using the ELF loader and loading it into the MIPS VM. And then the VM itself will run that compiled program. And the result of that compilation is the execution trace that is generated for the prover. So over here, as our first step, when we're running the program and collecting the trace, we'll get a sequence of MIPS instructions as an output. And so all of these instructions on the left side here are the compiled down program, and each row represents each separate instruction. So after we execute each row, we will get a value for each register, which is shown on the corresponding trace table on the right. So for example, row I says, I'll add the value in register 5 to the value of register 6, and then store that in register 7. And we can see in the corresponding trace table in row I that indeed, well, 13 plus 21 is 34. So this is a bit of like a simplification of what happens under the hood, but essentially just like as an overall view, what happens is that the program is compiled into these individual instructions, and then these instructions will be run individually, and then all of the results will be stored within the trace table, which can be found on the right side over here. And after we go through all those instructions, we'll get our complete execution trace, and that's given to the prover in order to generate a proof that our program was indeed correctly executed, and that all of those instructions in which we executed step by step are valid. And as part of the prover, we're going to go through these following steps. So first, our trace table that represents our execution trace is split into individual segments over here. Those are just smaller sequential executions from our original program execution. And then the segments here are divided into smaller sections into modules. And the instructions for each segment will be divided into based on their operation. So for example, we'll have 4 modular tables right here, one representing any arithmetic instructions. So any instructions over here that have any arithmetic-based operations would be stored into the arithmetic table. And then any kinds of, for example, logic-based operations, those instructions will be stored into the logic-based table and so on. And then from here, we're using the Stark protocol, and we're proving these modules independently with a protocol called Fry. And over here, we'll generate Stark-based proofs, and we'll have the arithmetic, memory, logic, and control proofs that are corresponding to their respective tables all generated. And then we'll use a lookup protocol to basically combine these modular proofs into a single proof for each segment. And it basically just is able to show that a segment is contained in a modular table and is able to prove that all of the program instructions were correctly verified in their respective modular tables. So we use a lookup protocol from there. And then we use a Plonk-based protocol. So compared to Stark, Plonk is a Snark-based, and all of those segment proofs from what we've seen in the previous step are recursively combined into a single continuation proof. And that single continuation proof proves the correctness of that entire program trace. And then from here, this step is optional, but if you would like to do any kinds of on-chain verification or EVM-based verification, for example, like deploying encoding your verifier logic on a smart contract and deploying it on Ethereum, you would have to make this final continuation proof into an EVM-friendly format. So Grot16 is one such way to enable for on-chain computation, and it provides a proof that's in constant time for verification, and that enables the final proof to be verified on the L1. Just because some of the other proof formats that we've seen, like with Stark-based proofs, for example, those are a bit too large to be efficiently verified on the L1. And so all of those steps that we've seen with dividing the program trace into modules and in segments, and then doing all of those tricks with first doing the Stark proving and then the Planck proving, and then finally wrapping, doing the Stark to Snark wrapping into Groth16 to enable for on-chain verification. All of those steps are really just to make the final proof more succinct and very short and in a compressed format for the verifier to verify. Because the idea is that the prover does all of the heavy lifting and the verifier just has to simply verify the proof. And the verifier could be it could be anyone. It could be just a user. You could do it on your phone. The idea is that anyone could be able to verify it. And so from here, that final proof is our Zyren proof that represents the proof of the correct execution of the program. And after generating our proof, the verifier contract will be able to verify on-chain the result of that program using the proof. And you don't have to do this on-chain. Zyren also provides some off-chain verification options as well. And we'll talk a little bit more about that later in this workshop. So now for the demo. We'll be walking through the project template, and the project template is just an easy way to spin up a new application using Zyren. And within the project template, there are some host and guest programs that are written in Rust that you can use. And we also have some example contracts that you can use to deploy the proofs that you generate on those contracts. And in terms of the proof generation, we have a few different proof types available if you're using the Zyren SDK. So we have Stark-based proofs and also EVM-compatible proofs, including Planck and Groth16. The Groth16 format is recommended for the EVM compatibility if you wanted to do some on-chain verification. You can also, for proof generation, choose between local and network proof generation. So local proof generation is just generating your proof on your local hardware. Network proof generation involves outsourcing your proof to the ZKM prover network, and we'll do the proof generation for you, and all you need to do on your side is the verification. And for the proof verification as well, we have the on-chain and also off-chain options. And then with the project template, you can use that for initial experimentation, but then you can also integrate it with any kind of ZK application that you'd like to build. So the link is right over here, and I will be doing a quick demo of that in a second. But just to give an overview of the general flow for the project template, we can see that we have those three main stages that we talked about when we were giving some details about what's happening under the hood for Zyren. So we have our program execution, and then our proof generation, and then our proof verification. So first, we can build our guest program either in Rust or Go, and from there, we can write our host program, and from there, we can either choose local or remote proving, so local or network-based proving, and then generate a verifier contract. And in terms of some more details in these stages for the program execution, when we're writing these programs, there are two main programs that you would have to write for your application. One is the guest program, one is the host program. The guest program includes all of the logic of the computation that you're trying to do. So we'll be going into the Fibonacci example in a second, because that's part of the default proof generation as part of the default template. But for the guest program, it will encode all of the logic for that computation. So for example, for the Fibonacci example, which we'll see over here, you can see that it has all of the logic that's associated with generating that Fibonacci number. So we'll have reading the input n from the host. So the input n is just the nth Fibonacci number that you'd like to generate. And then we're actually doing the computing of those Fibonacci numbers and then wrapping that result. So the guest program itself will include the program logic of the actual computation, and then we'll also execute that compiled ELF that is proven inside the ZKVM. And the host program, on the other hand, is more of the environment. So it will set up the environment for the guest program and evaluate the results from its execution. So in terms of the interactions between the guest and the host program, the host will provide inputs to the guest program will read those inputs, and then the guest program will write some private outputs. The host evaluates those private outputs that's provided by the guest, and the guest will commit public outputs, and the host will evaluate them. So we'll go into some more detail of what these guest and host programs look like in a second. But for now, we'll go into some of the more details relating to the different stages that are part of the project template. So for the proof generation stage, we have, as we mentioned, two types of proving. We have local proving and remote proving. So for client-side local proving, that's generated on your own hardware. If you meet those hardware requirements, which we have on our docs, you can feel free to do some local proving. It may take longer depending on the hardware that you have, but local proving may be good if, say, you're building some privacy-based applications and you'd rather that everything be kept locally, then doing the client-side proof generation may be more preferable. And then on the other side, there is server-side proving. So say that you have anticipating a larger demand for the amount of proofs that you want to generate, or say you don't have the hardware requirements that are needed for the local proof generation, it may be more preferable to use the server-side or remote proving. So you can just outsource your proof generation to the ZKM proving network. And if you want to get access to the proof network, just head over to zkm.io/apply and then apply for a spot, and you'll receive access based on the address that you specified, and be able to use the proof network. And in terms of proof verification, there are two main verification types that you can do with Siren. So for verifying on-chain, we have, as I mentioned, some pre-existing contracts that exist with the project template, and you can verify your validity of your generated proof by encoding the verifier logic to a smart contract, and we have an example script for that for both a Plonk-based verifier logic proof as well as a Groth16-based verifier logic, and then deploy those scripts on the L1 itself. And your verifying key is very important in this case. It's used to generate that on-chain verifier, and it's the contract it's the key that verifies that the contract is tailored to your specific ELF. So that way you know that your contract is corresponding to the appropriate proof that you want to be verified. And then your deployed verifier contract with your posted proof will determine if your proof is valid or invalid based on your verifier logic that was encoded. And the other option is verifying your proofs off-chain. So we have two ways of doing this for Siren. One is doing this via WASM, so in-browser proof verification. You can use some WASM bindings that are wrapped to some verification functions. And the other way is just doing some doing this via bare metal environment with the no STD environment. So going into the demo itself, I will switch my screen. And so as the first step, if you want to follow along or use the project template, head over to the link I showed, the ZKM project template link, and clone the repo there. Over here, you can also follow along with all of those steps that I have pasted here on the README, and it's also within the quick start section of the docs. But when you first come across the project template, you'll see three main directories. We have the guest directory, which houses the guest program implementation, the host directory, which contains the host, the main host application, as well as the contracts directory. And that includes some example scripts that encode the verifier logic, which we will deploy on a smart contract, some sample contracts, as well as some sample test contracts as well. And the test contracts are just to make sure that you can do the verification and that you have the proper proof to be verified before you spend on gas costs. And just to note, if you would like to use some network proving and using the ZKM prover network as opposed to local proof generation, you can make that adjustment in your ENV file. So over here, right now we have our settings set to local, but if you want to use ZKM's prover network and you have your address already whitelisted, all you need to do is change this to network. And then also specify the key, the private key that is associated with the address that you have whitelisted, and then generate your SSL as well. And you can follow the instructions on this page of the docs in order to configure this for the network proving. For now, I'll just keep it as local. And over here, when we go to, for example, our guest program, this is the same guest program that we saw in the example slide, and this is for proving the execution of a Fibonacci sequence. So this is a typical toy example. And just over here, as we can see, the guest program is encoding the logic of the computation itself, so including specifying what Fibonacci number to compute, and then encoding those public values of the program and committing those public values for the host. And then if we look at the host implementation over here, we see that first we have an argument to set up the prover client, and then setting up the inputs, executing the program, reading the outputs. So the outputs that should be read are the nth Fibonacci number, as well as the corresponding Fibonacci number to the nth one, as well as the one preceding that. And then over here, we can also print the number of cycles, and this is very useful, especially if you are making an application on Zyre and you want to pinpoint what specific parts of the program are taking up the most number of cycles in order to see which parts you could further optimize. This can be helpful. And then over here, we just have some logic for generating the core, compressed, and on-chain Groth16 proof, as well as the Planck proof as well. So there's a few different proof modes that you can use. The core mode, compressed mode, which will generate Stark proofs. And then for Stark-based proofs, we have the Planck and the Groth16. So that's a bit of an overview. And if you say, we would say for best practice, before you go on for proof generation, if you want to make sure that your program is behaving as correctly as you correctly anticipate, you can just execute it first. So just head over to the host directory and then run cargo run release execute. I typed in the wrong argument here. So it should be release and then execute. And again, all of these commands that you can use with the SDK can be found in our docs. So as you can see, some of the public outputs that were outputted were the Fibonacci, the nth Fibonacci number that we wanted to compute. So in this case, it was the 20th one. And then we can see the corresponding Fibonacci numbers that are associated with the 20th, as well as the one preceding that, so the 19th Fibonacci number. And we can see that our program executed successfully. Our values are correct. It also shows the number of cycles generated. So from here, we're ready to generate the proof itself. And if you say wanted to generate the core proof, the command for that is cargo run release and then core. And this will generate a Stark proof. And it will be a lot quicker than the Stark-based implementation. So for the Planck or the Groth16 based, if you're not planning to do any on-chain verification, it is recommended that you generate a Stark proof. So as you can see, we have successfully generated that proof. And if you do want to do some on-chain verification, you can run this one. So cargo run release bin, and then specify the system that you're using. So it would be Gross16. Let me just type in, or instead of typing in that command, let me just paste it from over here. And again, all of these commands are within our docs, within the quick start section. So the Gross16 proof, because I am running it locally, it is going to take some time. It also depends on the hardware configuration that you have as well. But going back over here, we can see that this is an example of the Groth16 proof that we'll have generated. So it will contain your Fibonacci number, the values associated with that. In this case, the 19th and 20th Fibonacci number, our verifying key that will be used, any kind of public values, and the proof itself. So this is the fixture for the Groth16 proof. And over here, if we want to do some verification as well, what we can do is going over here, going into our contracts directory, and then we can first test to see using the test scripts that are available in our contract directory. And since we're using the Forge library for this, all of our tests that we wrote based on our test folder over here have passed. And then for the verification itself, we can run this command. So this command, the main arguments are the script that we're trying to deploy that encodes the verifier logic that is associated with the proof system that we're using. So in this case, it would be the script over here that's encoding the verifier logic associated with the Groth16 proof system, because we're trying to verify the generated Groth16 proof. And then we specify the RPC URL based on where you want this proof to be deployed to. And so we're just going to deploy this to Sepolia as an example. And then we can see that our test or script has run successfully there. And as a result, we can deploy this directly on Ethereum and directly verify our proof from there. So those are the main functions that are needed in order to use Siren. And if you have any troubles at all, please feel free to contact us. I believe that there's a Discord as well, and I'll also send you guys the contact information, and any kinds of questions, please feel free to let us know. But overall, the project template is a good way to just get started with Siren and start experimenting with using our tooling, and then also just the processes for, say, creating that host and guest program, and then generating that proof, and then verifying it. So it's a good way to just get started with using Siren. And going back to our presentation over here, as a discussion of some of the use cases that you guys can think about when you're creating your solution for the hackathon. So one example, as I previously mentioned in the beginning of this workshop, could be, say, like an asset transfer example using entangled rollups. So the premise of entangled rollups is that it consists of these L2s that can serve as interoperability mechanisms for cross-chain transfers, but without having to implement the architecture of an actual bridge. So, for example, this displays the universal L2 process, and between Ethereum and Avalanche, without having to implement a third-party bridge between. So if we're sending 100 USDT chain from our source chain, let's say that's Ethereum, then we'll have that be deposited onto the L2 that's corresponding to our source chain. And then we will have a proof that that 100 USDT was burned on that L2. We'll have that proof generated off chain. And then the proof would be verified by a verification contract on our destination chain. So in this example over here, our destination chain is Avalanche. And once that proof is verified, it will automatically unlock those funds to the user on the L1. So in this case, we're using ZK as those ZK proofs as a cross-chain messaging mechanism. And in this case, we don't need to use any kinds of bridges that have its own kinds of security and trust assumptions involved. And another use case that ZKM is working on is Goat Network. Goat is the first L2 on ZKM's entangled rollup network, and security is inherited from the underlying L1, which is Bitcoin, instead of a third-party bridge. That's the main value prop behind the entangled rollup network. And it is a Bitcoin ZK rollup, and it has an inbuilt sustainable Bitcoin yield generation mechanism attached to it. So in that way, you can generate yield for your Bitcoin no matter how much you hold. And Goat uses ZKM or Zyron to generate these proofs of blocks on demand. And there's also proof verification that uses the help of ZK via BitVM by implementing these verifier scripts. And BitVM, the paradigm itself, is just an optimistic verification paradigm for enabling for arbitrary computations, like, for example, a Groth16 proof, and it uses ZK for this. And in terms of any kinds of other examples, we have some toy examples within our examples directory in the main Zyron repo. So you can check them out using this link over here. And we have a bunch of different examples that you can go ahead and try just running cargo run release. And over here, like, for example, we have a Bitcoin-based example. We have a Go example. So the examples that we showed over here and all the remaining ones are written in Rust. But if you wanted to see a Go equivalent, or if you just wanted some examples of how you can develop your own Go application using Zyron, you can reference the simple Go example here. And then there's also a cycle tracking example as well. Being able to generate a proof for the number of cycles that you have calculated for your given application. And so as kind of like an in-between example between our toy use cases as well as a full-fledged use case like with Goat Network, something more approachable but still like an end-to-end integration example can be ZKPDF. So ZKPDF was developed by the PSC, Privacy for Stewards Ethereum team, and essentially it's able to prove any kinds of information from PDFs that have a digital signature attached without having to reveal all those contents from the documents. So say that you have a document, a PDF document, it has some sensitive information that you just don't want to be revealed. Say that it contains perhaps like an address or some other kind of sensitive info. And in this case, since users have the ability to choose what is revealed and what's not, it's an example for a selective disclosure use case. And basically, we just swapped the Zyron ZK VM as the main proving environment. And you can go through this whole workflow of uploading your PDF, verifying the digital signature of your PDF, and generating your proof of your the PDF content using the ZK PDF example and running this on the Zyron backend. And you also have the option to generate proofs either locally or using the Zyron proof network. So if you want to see what an end-to-end use case example looks like, feel free to head over to this repo over here. And for creating your own use cases, there's many different kinds of areas that you can look at. Those that are within bridging or scaling, such as the entangled rollup use cases that we looked at, or even those that are related to governance and identity verification, or even those that are privacy related, are all examples of some domains of use cases that you can experiment with. And overall here is kind of the main resources that you need for getting started. So I would recommend that you first start off with the quick start and using the project template And for any kinds of questions or feedback that you have throughout the process, please feel free to submit an issue. But other than that, thank you so much for joining this workshop. If you have any questions, please feel free to let me know. I'll send the organizers my contact information for that. And Stefan, who is the lead dev of ZKM, and I will be there in person to help mentor you guys if you guys choose to use Zyron. And for any questions, again, just let us know. Thank you again so much for listening, and happy hacking.
Bueno, bien, espectacular. Ya sabemos, entonces tenemos ahí el bounty de la gente de Project ZKM. Pronto lo van a ver también en la página de Taikai. Tienen un bounty de $2.500, así que aprovechen, aprovechen. Bueno, ahora hacemos un mini break. Vamos a tener un workshop que es presencial desde la Dead House. Así que, nada, espérenos un ratito y seguimos con esto. El próximo es Mimic, así que nos vemos.